Good evening, welcome to Lecture 6 of Topic 2 of Unit 4, Young's Experiment. This video will be covering the main ideas of Chapter 11.1 of Book 2. Go back to Book 2. Please complete this reading before class. Here are the learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the KS table down the bottom right there. Okay, so having a look here, we can see we're after that students will be able to recognise Thomas Young's experimental data and explain how it demonstrates that light has a wave nature. So there's a couple of things there. I've tried to elaborate that out a little bit. Identify firstly Thomas Young's experimental data. You've got to be able to recognise it. Then explain how the experimental data supports wave theory. So in terms of knowledge, well, what was Thomas Young's experiment? If we don't know what it is, pretty hard to recognise it. How does the data support the wave theory of light? That's a pretty critical part there. And so you should ask yourself, can I recognise it? Alright, so in science, there are a few big names. They shake everything up, they're looked back upon with a bit of hero worship. Nowadays, most people, not just you guys, but most people would have heard the names Einstein. Many people would know of Hawking, if not by name, definitely by description. And a considerable number would know of people like Brian Cox or Neil deGrasse Tyson from media, things like TV shows Cosmos and specials that Brian Cox does. In popular media, these names are pretty big. In their relevant fields, these names become very significant, sometimes to the point that going against them becomes a bit akin to blasphemy, unfortunately. Around 350 BCE, Aristotle wrote a lot about motion, and if you've done my lectures on kinematics, you sort of hear me talk about this a bit. And he didn't actually test anything, he just wrote. He used his reasoning and logic, because that's what the Greeks are really keen on. Galileo and Newton came along nearly 2,000 years later and actually did some testing, and Aristotle's ideas were put aside. It was sufficient that because Aristotle wrote it, or Aristotle said it, that was sufficient evidence. Now, Newton did a lot of work on motion and light, and he came up with the idea, and he was pretty confident in the idea, that light was a particle, and they were called corpuscles. You don't need to know the name, but Newton really liked the idea that light was a particle. And his observations about ray diagrams that we've seen and dispersion of light was coherent with this proposal. Okay. And everyone had a very physical view of the world, that everything that we could see was caused by something, and so the idea sort of stuck around. And because Newton did so much work, this idea was held in such high esteem. Okay. Even though Huygens, or however I may correctly pronounce it, with his wave models and all these other things that they were starting to discover, like diffraction and interference, no one wanted to go against Newton's idea. We saw in Unit 3, in Topic 3 with our study of waves as it relates to sound, and Unit 4, Topic 2, that we started with the wave nature of light. Light has a lot of wave properties, and some of these can only be explained using light as a wave. Sorry, there's some of Newton's stuff and things that it couldn't do through the middle of the 18th century. Then we get to light as a wave. In the 1800s, Thomas Young presented a paper about sound waves with destructive and constructive interference. Remember, destructive interference is where two waves of the same amplitude cancel each other, and constructive is where they amplify each other. And he proposed that, well, if light was a wave, it should do the same thing. Now, we've seen interference patterns. Remember, they're those things where you've got multiple ripples coming out from it, and that they cross over, and you get bits where it's really high and bits where it's quite flat. And so he set out to do this as an experiment. He said, well, if light is a wave, and sound is a wave, and sound does this, then light should do it as well. And he set up a pretty straightforward experiment. I'm going to try to do this in class sometime, where he had a pinhole, and he had basically just a ray of light coming from it. Now I'm going to try to do it with a laser beam, but he just used a pinhole in a shade to get a thin collimated beam of light, and he put a piece of card, like you can see here in the picture, in the middle of it. And so you got half the light coming on one side, half the light coming on the other side. Often this is now represented as a wave of light hitting two pinholes to create two new sources of light, but this is how Thomas Young did his. And instead of seeing two spots, so spot on the left and spot on the right, he saw this, an interference pattern. Okay, so we've got one bright one in the middle, but how could we have a bright one in the middle? That's where the card is, and then we've got two either side of it. Oh, well, those could be those two, but then we see, then we see more either side of it. So that's an interference pattern. Okay, light as a particle just could not explain this, but light as a wave could. Okay, the bright parts were constructive interference, the bright spots. The dark regions, the bits in between the bright spots, were destructive interference. Okay? And this was very conclusive evidence to put light particles back in the coffin, and everyone was on the wave bandwagon going into the 19th century. Okay? Now this image is out of the textbook. Here we can see the wave of light approaching the two holes, and we can see the two waves spreading out from it and these patterns appearing inside. And this is what we just saw in that red laser image there. The bright spot, either side, and up here we have the intensity graph. Okay, that's this bit here, really common in being presented to students. So that's the Thomas Young's experimental evidence that you need to recognise. The only way this happens is two things. One, as the light comes through the hole, it has to diffract. It has to spread out in these arches like we see down here. And secondly, light has to be demonstrating both constructive and destructive interference. So here are the two things. One, we have to have some diffraction occurring. And two, these multiple bright spots instead of just two. So we're getting constructive and destructive interference. Okay, so this is the data that explains light must have wave-like properties. You can't do it with particles. Okay, so Thomas Young was like, cool, we've got light as a wave. Or is it? Now into the 19th century, Max Planck, Niels Bohr, and Albert Einstein provided some issues with light as a wave, and that's going to be the rest of our exploration through quantum mechanics. The idea that, hey, we proved that it's a wave, and now we're going to prove it's not a wave again. Bugger. Okay, so we're going to get a little bit of both sides going on here. So, pretty straightforward short lesson. So in the video we've looked at the following. Firstly, what was Thomas Young's experiment? Secondly, what was the result of Young's experiment? And thirdly, how that proved that light behaved as a wave. Okay. Now, for your entrance to class, please complete questions 1 to 9 in chapter 11.1. Check your learning PDFs from book 2, not book 1, book 2. If it doesn't say stuff about light waves, you're in the wrong place. I believe 11.1 from book 1 is motion. For your entrance to class, complete those questions at 1 to 9 and put it into 4.2.6 on eLearn. Thanks very much for listening, guys. Have a great night. Bye.